We have done already introduction of the differential equation in the last lecture. Also, I have given the classification of the differential equation, that we can take the order of differential equation, degree of differential equation, linear, nonlinear, and geometry of the homogeneous or non-homogeneous, and also we discuss the partial differential equation, ordinary differential equation. Mostly we are going to discuss the ordinary differential equation. Now today's lecture, I'm going to give you the origin, where we get the differential equation. There are two types of origin. One is the geometrical origin, and second is the physical origin. So I give you the example for the geometrical origin. In geometrical origin, we take the, for example, we take the equation, number one I take here, family of curves. A family of curves we can define. For example, we have the straight lines. We write the family of curves as C1x plus C2. These are family of curves. For each value of C1 and C2, we get an equation of the line. So C1 and C2 are constants. We call C1 and C2 as arbitrary constants. C1 and C2 are arbitrary constants. They can have any values. They are real numbers, and we can give any value to them. I will explain you that how we get the values for that one. But first, I'm going to tell you how we get the differential equation for the system of for the lines, for straight lines family of curves. I differentiate this one. I get dy by dx is equal to c1. Derivative x is 1 and derivative constant is 0. So it's I want to remove the constant from my differential equation, and I will call that's the differential equation for the family of curves. Here is a differential equation, but this C1 is existing, so we want to remove it. We differentiate it again, so we get here d2y by dx squared is equal to 0. So this is the differential equation for the family of curves. This family of curves is straight lines. So that's how we can remove the constants, and then we say is the differential equation and solution of this differential equation will give us straight lines. So that's the idea that's behind this. Is the first example I'm going to take. I take another family of curve, and this family of curve I'm going to have the exponential form, and this is not the straight line as I mentioned here, different from this one, and we can see that how we can rewrite this one in terms of the differential equation. So I have the family of curve given by y is equal to c e to power x squared by 2. So this is my differential equation. This is my equation, geometrical equation. I want to write this one as the differential equation. We need in this course skills for derivatives and also skill for the integration. You have to revise this portion, and if you are good in differentiation and integration, it's very easy for you to solve and to understand the differential equation. Again, I take the derivative of this one with respect to x. We get here dy by dx is equal to c is a constant. I have the derivative of e to power x squared by 2. And derivative of this one is c1. Derivative e to power u is e to power u. U is my x squared by 2. And then I get here d by dx of x squared by 2. And this is my integration we're having here. This as, again, we're having c1, sorry, not c1, c dot e to power x squared by 2 into 2x over 2. So 2 is considered 2. So I get here x into c1 e to power x squared by 2. Now I can see it here. You can see this e to power x, sorry, here c, not c1. And this what? This is my y. So I can write my dy by dx is equal to this c e to power x squared by 2, which that is my y, so this is my xy. So it's my required differential equation for the family of curve. So I take another example, and I can explain you. You remember this one thing, that we have in the one constant, and we have the equation of the equation is a first order differential equation. In the last example, we get two arbitrary constants, c1x and c2, and c1 and c2 are two constants, so we get second order differential equation. I take another example of the family of curves, and we solve it, and we see how we get the differential equation for that one. There we will get here in this new example which I'm going to define here. This here is equal to C1, y equal to this family of curves given by C1. This is my third example. Y is equal to C1 e to power 2x plus C2 e to power minus 2x minus 3x. This is my differential equation. And I'm interested to find the differential equation for this family of curves. So how many constants we have? We have two constants. This means we will get the differential equation of order 2 because there are two constants. One constant we get differential equation of order 1. Two constants we get differential equation of order 2. So I take the first derivative. I get here dy by dx is equal to, again exponential, we take c1 e to power 2x, and then derivative of 2x is 2 plus c2 e to power u is minus 3x, and then derivative of minus 3x is minus 3. I rewrite this one. I get here 2c1 e to power 2x minus 3c2 e to power minus 3x. So as I mentioned that we can have here, because our differential equation is of order having two arbitrary constants, it must be of order 2. We take a second derivative. So I rewrite here d2y by dx squared. Again we are having here the value of the derivative. I says 2c1, this is my constant. Derivative of this e to power 2x is e to power 2x. And derivative of 2x is 2 minus 3. c2 is constant. Then we take the derivative of this one. It's e to power minus 3x into minus 3. So I rewrite this one. We get here this is equal to 4 c1 e to power 2x minus minus plus 9 c2 e to power minus 3x. Now I can write an equation which contains d2y by dx squared and dy by dx, and that can help me to write my differential equation, that is equal to, if I substitute these values in this equation, d2y by dx squared plus dy by dx minus 6y is equal to 0, then these are satisfied. We can check it here. Then we substitute the values. What is going to happen? d2y by dx squared is 4 c1 e to power 2x plus 9 c2 e to power minus 3x. Then dy by dx. dy by dx is 2 c1 e to power plus 2, I will write, e to power 2x minus 3 c2 e to power minus 3x. Then minus 6y. I multiply here by minus 6. I get here minus 6 e to power 2x, and then plus 6 minus 6 again, because multiplying with minus, I get here minus. This become minus 6 c2 e to power minus 3x. Now we add this one. We get plus 4 plus 2 is plus 6, and minus 6 becomes 0. And 9 plus 9 minus 3 minus 6 is minus 9, and that's equal to 0. So this is equal to 0. We say that this is solution of this differential equation. So required differential equation is for this family of curve is d2, the second order differential equation, d2y by dx squared, and then we are having here plus dy by dx. We have the differential equation d2y by dx squared plus dy by dx minus 6y equal to 0. We can have many different situations, the family of curves, and we can have, for example, sine curve, cosine curve, different type of the curve, family of curves, and from there we can write our differential equation. It can be 3 variables, 3 arbitrary constants. We will get here third order differential equations. 1 arbitrary constant, we get first order differential equation. 2 arbitrary constants, we get second order differential equation. 3 arbitrary constants, we get third order. And we have n arbitrary constants, we get nth order differential equations. So this was the idea that we're having the geometrical origin. We have already done the first part of this one, that was the geometrical origin, and we take the family of curves, and with the help of family of curves we just develop the equation of the differential equations. And I am going to show you now the physical origins. The first one, the physical origin, we take here the free falling stone. So one thing you must remember, that we having one rule which is applied in equations, I would say especially where there is a motion. That is Newton's second law of motion. And this famous one is F is equal to mass time acceleration. We take the acceleration y as a function of t, so we can write this one as F is equal to m d2y, acceleration is d2y by dt square. Or we can write this one as d2y by dt square is equal to F over m. So that's most important differential equation in the whole set, and the rules which are, because this rule is applied everywhere where is a motion. So mostly when we're going to study the differential equation of second order. So please note this one, don't forget it. Every type of motion is being organized by the Newton equation of motion given by the Newton's second law of motion. So similarly, we take the falling stone. There's a stone here as falling down, as having certain mass, as moving with the acceleration due to the gravity, and we can write the differential equation if we take s as a distance. As a distance, the function of t. So we can write here d2 s by dt square is equal to g. We say mass is equal to 1, and we take gravity downward. We say it's negative, so we take here it is minus. So this is my differential equation, which is going to give me the motion of a falling stone. We can have here the second example I'm going to take. In the second example, I am going to take here the spring vertical displacement. Spring vertical, again this is a motion. And when there's a motion, as I told you, we'll be organizing it by this one. This is equal to m d2y by dt square is equal to minus ky. Y is a displacement. Y is displacement of the spring, of the motion of spring, displacement. And then we're having here m is the mass, as I mentioned before also, m is the mass, and k is spring constant. K is spring constant. So again, as I mentioned, that always we get the motion by the second order differential equation. So this is the idea we're having here. In the case of the spring displacement, I take one more example and tell you how we can write the example for the physical origins, and then we can obviously predict it. And we're having our physical origin now is a electric circuit. We use here this number 3 RLC circuit, and we use here the Kirchhoff's second law of motion, which shows second law of motion. Second law. Using this law, we can write the equation is L d2q by dt square plus R dq by dt plus 1 upon c q is equal to E. So we can see here what are the values we are having here, where q is a charge in capacitor. Q is charge in capacitor. We give the charge in capacitor. And number 2, we having L. L is inductance. L is inductance. And then we having here C. C is capacitance. C is capacitance. And then we're having R. R is resistance. R is resistance. And we are having here E is voltage. So definitely our electrical engineers will be using this in their course. Many times they will be using this one. Mechanical engineers, they are going to use these equations many times in their course. So these are the 3 examples for this one. We are having very important example also in mechanics. That is the example related to the motion of spring pendulum. So we have the pendulum, which is motion, and we can just describe its motion by the differential equation, and it's my fourth example, and that's here is the motion of the simple pendulum. Motion of simple pendulum. We know this is our pendulum. It's vibrating here. This is the length of the pendulum. This vibration is like this one. And here it's moving, the ball is moving, and this is making here angle theta. And we can write the equation for this one is d2 theta by dt square is equal to is plus g over L sine theta is equal to 0, where theta, as I mentioned, is angular displacement. Theta is angular displacement, and then we are having here the L is length of the rod. This is my L. This here is my L. This length of the rod. L is length of rod, and these are all physical phenomena that we can describe in terms of the equation. G is the acceleration due to gravity. Or gravitational acceleration, we can say. So these are the ideas that we're having here. The motion of simple pendulum is also a mechanical engineering problem, that are the physics we're having also, the motion of the pendulum, and that's given by this differential equation. And we're having here the LRC circuit that's given by this equation, and we have many applications we can have, and we can write. So important in civil engineering, we are having here deflection of beam. It's a different equation, that's why I'm mentioning it here, especially this very special differential equation, which is not of second order. So it's a fourth order. We're having here the fifth example. I said I'm especially going to mention this one, that is here deflection of beam. Deformation of beam. And we're having EI is d to 4 by dx power 4 is equal to f of x, where E is the Young's modulus. E is Young's modulus. I is moment of inertia. And we are having here f of x is load per unit length. Due to this load, there is a deflection on beam, and we can study with the help of this equation. So these are the 5 equations in our science and engineering that we can solve this one. Then there is very important applications of the differential equation. We are going to study that one also. And this is number 5 example for me, a physical origin. That's a growth and decay. We can have different models for growth and decay, and we can just understand and predict it, reproduce it with the help of this equation, especially the bacteria model, and especially when we're having this called COVID-19, and sometime we need to predict that one, but with the results after 5-6 days, after 4 months, we use this equation. That is number 6, growth and decay. Growth and decay. The equation for this one is dP by dt, this first order differential equation, is equal to K times P, and with this one we having initial condition. I will explain you that the value at some initial time. So we can have here this as initial condition. P is the given quantity. It can be population or anything is given quantity. And K is the constant of proportionality. So we are having here this rate of change, we say dp by dt, is proportional to the p, that's the population present, this is p. And then from there we solve this one, we get the value of k, we get exponential solution. And from there we can predict what will be the result after some time. And then parallel to this one, we're having Newton's law of cooling. Newton is in heat problems we're having, especially in the case of we discussing the mechanical engineering. There we need it, Newton law of cooling. So also we will take as an application in our differential equation and we'll solve some problem for that one. This is dt, t is the temperature, and the small t is time, is proportional to the difference of temperature. And this is here is Ts, the surrounding. So this here, the rate of change of the temperature is different, proportional to the difference of temperature. K is a constant of proportionality. T is the temperature. This is T minus T0. T minus T0, Ts. T minus Ts is our temperature difference. Is temperature difference. K, as I mentioned, this constant, T is the temperature. So there are many other applications. We can have the projectile, we're having the conduction of heat, we're having isolation of electrical systems, we're having rate of decay of radioactive substance, and growth of population, fluid flow. With these have all these applications. They're being solved, the situation is solved with the help of differential equation, and then we use to predict them and to reproduce the situation. So that's the idea behind them, and we'll study how we can solve the differential equations. And we'll discuss the solutions. I'll give you more introduction for that.